So we'll quickly see linear regression in this sort of single machine setting with Scalable under our belt so far. Am I online, Don? So this is called ordinary least squares regression. Well, I don't know how useful this is, but so here's a bunch of points, so you have hand size and height. So I guess Trump is somewhere here. I actually don't know how big it's supposed to be small. So and then so these are some individuals, right? And then all we're doing is fitting this line, and so the main parameters are this 5.0, which is the y-intercept, and the other parameter is 0.81, which is the slope, right? So we multiply hand size on the x-axis with the slope and the intercept, and then we explain the height. So this is classical regression, and originally it's attributed to Galton, Sir Francis Galton, what was he trying to do? He was trying to explain the heights of soldiers in the British Army or some army, I don't remember. And he called this the regression to the mean because, and the word is somehow stuck. Yeah, and what's the main idea? Of course, there's a lot of lines here, so you can change this. I'm not sure how. I guess we can change the points, right? So the lines move. So why are we getting these lines? So these lines, this particular value 0.59 and 0.79 for the intercept and the slope are coming from a principle which you will learn in much more detail in the foundations course. It's called the maximum likelihood principle. And but we can just view at it from an optimization point of view. So what we are saying is that this sort of best fitted line is one that minimizes the area which is given by the square deviation from the actual observation. So here's a point. This is the deviation from the line, and this is just the square of that side. So that's the sort of one square, telling you how far this point is. This is another tiny square, and so on. This is a really tiny square because it's almost on the line. So and then you sum up all these areas, and the best fitted line is the one that minimizes the sum of all these areas, and that's called ordinary least squares. Or okay, I think that's what. And in 2D, you see it's a little basically the same idea. So if you have points on two axes, x1 and x2, so you have two features, and then you're still trying to predict the same y. And so now instead of a line, so you're only seeing this line as a projection of this plane on each coordinate, right? That's what these lines are. But the actual data sits in the plane, right? In x1, x2. And then what you're now seeing is that the deviation from each point to the closest point on the plane, right? So that, and then you again have a sum of squares, and the same principle applies. So it's same idea works in general. And of course, here you have, so you have the, let's see, if you have a plane, you still have the z-intercept, right? And then you have the slope along x1, right? And then the slope along x2. So that's the only, so you have, and usually these are called betas. Beta 1, beta 2 are these called slopes, and then beta 0 is usually the intercept. Okay, so I don't know, this looks cool. Susan Boyle. I have no idea if Susan Boyle is. Okay, so it's just a quick recall, Stats 101. So it's called ordinary least squares regression. I won't, you guys can watch this. Amit explains this in the same notation, but I think you really should watch this if you want to really get into how distributed linear algebra works under the hood, right? Because he explains how you can do this least squares regression for certain shapes of matrices, even though they're really large. In particular, the number of features is, few hundred, thousand, whatever it'll fit in a machine. But then the number of rows is incredibly large. Like you have, like, say, a population of, I don't know, Europe. So you can still do linear regression in this distributed setting that I'll give you a flavor of soon. So that's what he's trying to show here. So we have our matrix A, which is in R to the M cross D. So you have M rows and D columns. So that's kind of our sort of information, our data usually. So D will be the number of features. And yeah, I think I will skip in the interest of time, and I strongly recommend you watch it, especially if you've not taken any stats courses like Don, and I don't know how. So there are these notions of penalty that you need to have for model complexity. I don't know. Should we watch this? What do you guys think? It's very fundamental. Okay, so I'll just explain quickly. So what happens is when the weights are allowed to be arbitrary, the models can get too complex, right? That means they can start fitting things too well in some sense. Then you usually have some kind of regularization or penalty for model complexity. This is a typical regularization form. So you see what you're trying to do is minimize the weight, which are the betas I told you, the intercept and the slopes. This is our data. And then this is the actual what you're trying to explain, right? This is like the height, and these are various measurements of the people. So then, of course, you're trying to minimize the sum of squares. You're trying to find the weight that minimizes the sum of squares. But you are also, at the same time, trying to minimize this thing. So you take the L2 norm, or the weights themselves, how big they are, and then you penalize large weights by this tuning parameter lambda. Okay, so if lambda is 0, you're back to classical ordinary least squares, right? You don't care what the weights are, you're only interested in minimizing the sum of square deviations. But often we don't want that. We want large weights to be penalized because we don't want, large weights. So then that's one form of penalizing model complexity. Then you will have this tuning parameter lambda, and then you will have to do some kind of cross validation to find the optimal lambda. But for each fixed lambda, you will minimize this term. Okay, this is called ridge regression. This is one. There's another one called lasso, which looks at the L1 distance, the absolute values of the weights, and it actually gets into more interesting geometry and stuff. But we have to do some typical regularization. Okay. And this again is only for those who want to get into this gradient descent for least squares. So how do you find the weight that minimizes this loss? That's what this is. This one. So this is an L2 loss. So to minimize this loss, you would essentially set up a gradient descent algorithm, which basically will implicitly define this surface. So now we're in the space of weights, and we start with some initial guess for weights, and then we move down the path of lower and lower sum of squares with the penalty. Okay, so then we stop once the change in wi+1 in the next step is not that different from the current w. So that's the stopping rule. This is completely heuristic algorithm. If you start at the wrong place, you can definitely get stuck, but often it works. Okay. The nice thing about gradient descent is, I don't know if I have stochastic gradient descent. So why is this important? Because when the number of rows is so huge, we cannot directly apply gradient descent. Then, because the gradient descent is looking at all possible sum of squares. It means you have to compute this for every row. effectively. So then what you can do is you can basically take the data, partition it randomly into batches, and as long as the sampling scheme for each batch is uniform and the size of the batch is some ratio of the total size of the data, there are probabilistic guarantees that you will converge to the true answer, with a high probability. So that's called stochastic gradient descent. That's pretty much the workhorse of a lot of big data, including Google's TensorFlow libraries, deep learning, all of this stuff, right? And of course, that's easy now because you will only hit your, so it's, so now you have sort of, you look at some small tiny batch and, minimize the loss for that. It'll take you somewhere, and then you will, take the other subsample, which is another second batch, and hit it with the same algorithm. It'll take you slightly somewhere. So you'll kind of do this drunken walk, stochastic gradient descent. And once you go through all the batches, that's called one epoch. And then you can, do this multiple epochs, and then you will sort of be able to compute it even on large data. And generally, it will converge. Yeah.
If you have an analytical solution,
yeah.
Why do you need it, or why do you want it?
I mean, the analytical solution is not going to, it's still going to involve operations, arithmetic operations that involve all the entries, right? So it's not just coming out of...
So it's more efficient for the matrices.
Yeah, I mean, so, here's the solution, right? So closed form solution, you have to take X, transpose X, and X is like billions of rows, and I mean, how do you do this? So anyway, that's basically big data in a nutshell. I mean, that's all that's going on. I mean, okay, the optimization layer, right? And in fact, this algorithm gets repeated, revisited many times. And I think the papers showing this batch gradient descent are not that old. Does anyone know how old is stochastic gradient descent? It's not more than 5 years old, I think. I don't know. Or it's used heavily only in the last several years. Okay, so now let's kind of get our hands dirty with this Darren Wilkinson. I told you, this English statistician who's done all kinds of languages, including R, but he's got a nice blog on Scala. So let's sort of dive into his, so you can try this on Spark Shell as well. So that's his tutorial. So let's, so what is he doing? Quick introduction to Apache Spark for statisticians. It's quite good. So it'll walk you through all the steps. He's on some kind of Debian-based system. You have to install JDK, and then he's getting it from the EU, Spark 2.1. This is basically what I showed you. So once you download this tarball, you have to tar, extract verbose file, zip, and then give it the target, and it'll just produce this directory, and you can cd, change directory into there. And he's running Spark Pi. You can run whatever, Spark Shell, like a bin Spark Shell will be thrown into Scala. Okay, so so I think his tutorial is nice, but let's do it in Databricks directly. So in I can import Breeze stats.distributions.everything. So I now have at my disposal all these distributions like Gaussian, which is a normal distribution, and Gaussian 1, 2, and then I'm sampling 10,000, and then I'm turning this lazily defined Gaussian into an RDD, XRDD. So we can call the mean and sample variance methods and see what the mean is and what the sample variance is. So the mean is 0.98. So you see it's close to what I specified to be the mean of this random number generator. In the foundations course, we will actually not do this. We will actually start with modular arithmetic, define pseudo-random numbers, go back to the original method called the middle square method that von Neumann used to find a detonator for the US atom bomb in Manhattan. So we'll do things like properly, and I'll introduce you the inversion method of Gaussian random variables that Galton had when he was rolling dice in baskets in London. long ago, because you want to see where it's coming from, right? But for now, let's just black box this. And the sample variance is 4 because that's the input is this standard deviation is the second argument to specify. Okay, so it looks reasonable. Then
quick question.
Yeah.
I was just curious. I was trying to calculate the median as well, and the median is I mean it's difficult in a parallel environment, right? Is there any way of doing median?
I actually don't know. Did median work here?
No, it doesn't have it. So.
Oh, okay. So, well, we spent like, I don't know, maybe one whole week on sketching methods last semester, like computing median and t-digest and tail probabilities, because you need those things. Like median is one example. Yeah, so in fact, Ronald Fisher in 1921 already talks about the big difference between mean and median. And he didn't call this recursively computable statistics, but that's what he was saying. So for mean and standard deviation and variance, you can have a finite buffer. And as data comes in, you can update the mean runningly. That's what's probably going on with RDDs. I don't know. Well, actually, you can even map reduce from mean, right? You can just add everything and divide by the total size. But what Fisher already pointed out is to compute the median, you need to have an entire data set and then look at the inverse image of the 0.5 for the empirical distribution function. So if a new point comes in, you know, you have to basically do this. It's not recursively updatable, right? He had a different name for it. And there's a whole host of methods. In fact, one of the top conferences in randomized algorithms is happening in Uppsala this year in early June, called Analysis of Algorithms. And I think a whole session probably is devoted to these so-called sketching methods. So these are probabilistic data structures that give you, with very high probability, a very good accurate estimate of median or for fraud detection in this kind of application, the tail probability events, you know, like what is some score you're after, and then the score is in the extreme end, you know, say the left 0.01% tail. So for that, again, yeah, so we did something called t-digest in the course, but for that you needed structured streaming, and we won't descend into it. But if you want, I don't know if it's here. Let me see, I probably deleted it. So, you know, this is all up there for loading, you know, so let's see. So you can kind of get into that if you really want. So there's structured streaming. Programming guide is, you know, this is like 2-3 hours, at least maybe 4 hours. And then I sort of show you how to set up a structured streaming job by running a shell script that spits these files. So you pretend things are coming at you. And then there is this t-digest input stream. So it's one of these sketching methods that is used heavily in industry, but it's only for one dimension. So you do some magic and produce a score of how dangerous this transaction is in a whatever setting, or in a cybercrime setting. And then it'll simply flag those events that are in below some threshold using this t-digest method. But
can I find this out? Have a SDS2 too?
yeah, it's just go to 2017 and, you know, it's all there. And in fact, I should say that so this was done like kind of in the heat of almost some of my consulting work. And, you know, Benny Avelin and Håkan Persson, they are data scientists, more experienced guys at Combiant, originally trained in pure maths, PDEs. So they really improved this a lot. This is already kind of bleeding edge. So they do this flat map groups with states, and so now we're trying to do tree arithmetics on them, hopefully. But yeah, this is all there, and this is what we won't do today, because that's like another whole universe. So I'll do simple things. So we'll, well, yeah. So here is x2. I'm just defining, you know, another Gaussian sample, 10,000, centered at 0, variance or standard deviation 1. And then now you see I'm zipping x with x2, and I'm creating xx. So I'm creating, you know, 2 independent Gaussian random variables with different means and standard deviation. And then I'm taking xx, which the zip thing makes it a tuple, right? Like this. Then I'm simply mapping each point to 2 times, you know, so whatever is coming in, this p will be my tuple now. Whatever is coming in, the first element I multiply by 2, the second element I multiply by 1, and then I add 1.5, right? Why? Because this is my intercept. I'm generating data for regression now, the y values. This is my slope for the second coordinate. This is the slope, right? So now I have my sort of LP. I don't know why I called it LP. No idea. So then EPS is, now I'm going to add noise. So EPS is epsilon. So I'm taking a Gaussian random variable centered at 0 with standard deviation 1. And again, 10,000 of them. So these are my little noises I want to add around, because you see LP is just the plane, right? The linear plane. So I want to add noise around it to create my y values. That's what I'm cooking up here. So then I get my y by zipping LP with EPS. So this is just where my points downstairs hit the plane. And then I simply add them, right? Add the epsilon noises to the thing. That's all this operation is doing. And finally, I have my val yx, where I zip my y values, upstairs with the noise, with my xx values downstairs. So now I have my y, x1, and x2, right? So this is kind of my just sort of cooking up points for a regression in 2 dimensions. And so if I take 5 of them on just RDD land, I'll start seeing that here's my y and my x1 and x2 values. Did I do it in the right order? I don't know. Yeah. P21, P22, yeah. So this is y, this is x1, this is x2 with noise. So now what I'm doing is just turning this into a data frame with labels y, x1, x2, and showing the first 5 elements. And so now we can get into Spark ML libs regression, linear regression. Remember I showed you this programming guide which does so much more, including GLMs and so on, and logistic regression, but let's just tap into this one. And with these imports, I'm creating a new constructor, linear regression, called LM, and then I'm saying LM explain parameters, get standardization, set standardization to be false. So let's see. So yeah, when I first asked it to explain params, so there's a lot going on, right? It's by default using an elastic net mixing parameter in the range 0, 1. For alpha 0, the penalty is an L2 penalty. For alpha 1, it's a L1 penalty. There's a lot going on under the hood. Like, this is like a whole course you should take on linear regression and GLMs. And what else are we teaching in the stats program? Probably at least you need regression and yeah. Anyway, so whatever. There's something black magic going on under the hood, but just remember it's a penalty. It's a model complexity penalty. And then you can ask for it to have standardizations, which means it just removes the mean and divides by the standard deviation. And then you can dive into the docs to figure out and change settings and stuff if you need, but the defaults usually work okay. So here is my, so I transformed the data frame to the required format because, yeah, so I need this column called label. Remember, that's my y values, and I need this column called features. And features need to be, yeah, MLlib vectors, dense vectors. So that's all I'm doing. Okay, because that's really what the MLlib library expects. So now all I have to do is lm.fit bflr, so data frame prepared for linear regression, and I do fit.intercept, and I'm done, right? So I have my intercept is 1.408, and my coefficients for x1 and x2 are 2 and 0. This is, so recall this is close to what we set up, right? We cooked it up so that the intercept is what, 1.5 was it? And then 2 and 1 were the slopes, right? So, it's okay. And in the foundations course, we will see this. This is actually a specific instance of what's called the maximum likelihood principle. And this is called a maximum likelihood estimator. And it has this amazing property in finite dimensional experiments. This is a finite dimensional, it's a parametric experiment, right? Because you only have 3 parameters. The amazing property is that it's asymptotically consistent. That means as the number of data points go to infinity, it'll find the true parameters with higher and higher probability in a tighter and tighter confidence set. Okay, and to really understand that, you have to understand convergence and probability, which I'll also explain. So it'll be torture. No, it'll be animated, so it won't be too bad. Okay, but it's a very, very powerful idea. And in fact, all of Bayesian statistics is built on it. I don't know what is it a title? Some SUM? I don't know. Maybe something changed. Okay. So yeah, so I fit it, and then I call that the sum, and then I'm getting the R2, which is a statistic for seeing how well your model fit, R-squared statistic. So we won't really dive into all these details, but it has all these various statistics, root mean square error. Oh, right. So there's a lot of warnings. A pure expression does nothing in statement position. You may be omitting this. I don't know. Anyway, I really don't know. I didn't get these warnings before. Oh, yeah, now it complains it doesn't take any parameters. Anyway, I don't know what this is. We can fix this later. Do you know, Don? Okay, it's fine. A pure expression does nothing in statement position. I don't know. Anyway, so here is Darren's blog. So this gives you a little more insight, and I basically pulled a lot of this code snippets from here. So please get into this. So this is Scala, generalized linear models. So those of you who know GLM can really get into this. PCA and so on. So let's not too bogged down by that. So that's kind of a crash hurry of linear regression simulation with basic MLlib and RDD interface and things like this. Big data. Oh, right, that's the course. Okay, so I don't know what this is exactly. Oh, right. So, this is maybe extremely important. So those of you who want to, get into Apache Spark and really understand what's going on should read this 8-page paper, right? So it's about matrix computations and optimizations in Apache Spark. So especially if you've had a basic intro grad course in optimization and matrix computations, then this sets the stage for how to do these things in a distributed setting, right? So here is the big gang of guys. Mate is here. There's a big gang of people. Zadeh is this other guy, Stanford. So these guys are all part of this Shivram as well. They're all part of this AmpLab Berkeley gang. So yeah, distributed linear algebra, matrix computations, optimization, machine learning, MLlib, Spark. So they talk, and this is why I introduced RDDs. So you're seeing things at the raw level of RDDs. So we don't have abstractions and data frames and data sets. So they talk about singular value decompositions and principal component analysis, which is a fundamental sort of first tool of dimensionality reduction you would hit most data sets with. Convex programs, gradient descent. What is this? LBFGS? That was Ganan, Shano. There's a bunch of guys' names. It's another optimization algorithm. I think it uses gradient information. I'm not sure. LBFGS. I used to know all this, right? In Cornell, our textbook was numerical recipes in C. So we went through a lot of this. So anyway, I highly recommend reading this if you, especially, Marcus is interested in implementing your own designs for penalization, right? For your problems, this is where you want to get into, and eventually, if you're stubborn and spend a few 50 hours for last week, whatever, you should be able to make a Spark package and actually, share it with the community. Okay, so what I'll go through next very quickly is the various representations for distributed matrices, because that's fundamental. So we'll see about row matrix, indexed row matrix, coordinate matrix, block matrix, and those are the sort of heart of matrix computations that are behind all these more higher level arithmetic operations like SVD and so on. What is this one? First conic solvers. I actually didn't read that section. Yeah, so lasso regression was the one I told you, right? This is this L1 penalty, because see now the lambda, if you see this lambda expression, what you're trying to minimize is, again, the weights and the intercept are encoded, encoded here, and then you have your so this is all the notation is different. So y is b, I think, and a is the data, and x is the weights, the intercept, and then x is the same, the weights and the intercepts, and lambda is now our penalty term. But you see this has 1, this line and 1, which is now the L1, so it's the absolute value of the weights as opposed to the square of the weights, which was the L2 penalty we saw in ridge regression. This is like a big hit in stats for the last decade or so. Like, it was a big lasso bandwagon. People jumped in. It's actually really interesting. This was originally done by Tipshirani from Stanford. What's nice is when you look at the parameter space, the geometry of the parameter space given by this L2 norm, it has all these beautiful convex shapes. So what it does is for certain lambda values, the weights completely disappear. So you can basically forget about that coordinate, and it kind of makes a lot of sense and many problems. So that's very popular. That's implemented as well. What else? Yeah. So then these guys are into hardware as well, and network speeds and everything. So as I said, when you start doing this, so when I studied computations, matrix computations, I used this book by Golub and these guys. It's not here. So it's a standard book on matrix computations. But there the asymptotics are only 2 dimensions, right? Space and memory. Right? Sorry, space is memory, space and time. How much CPU time and how much memory does it take? But now in this world, they have to also worry about minimizing communication costs between machines. So a lot of that boils down to asymptotic justifications is tridimensional now. Okay, so once again, I'll let you watch this later if you want to get into this. So he really nicely talks about exactly what I said. Computation, storage, and memory, how to think about these things properly. And this is just my notes of the video. He also talks about big N and big D. So this is where he's talking about tall and skinny matrix structures that you can do certain things on. And for other problems, there's not a lot you can do actually. Okay, but yeah, and this one's on communication hierarchy. So things are very fast in random access memory, and then there's network and CPU. So we want to network currently is the main bottleneck in commodity clusters. Let's see, yeah. So these are for people who want to really get into Spark under the hood stuff. Yeah. And of course, if you really want to teach a course properly on this, well, teach or learn. In Russian, it's the same word, right? Teach and learn. Yeah, I like that. So I would love to do this for my vacation, but this is a great course. I think this is really what you want to get into. This is Reza Zadeh's course at Stanford. It's the notes are great, the student projects are great. It's if you really want to get into this after watching those videos and playing around, this is where I would jump in. Okay, so that's mostly prep for people. And I will simply show you what's in the programming guide. So how do I learn things that I don't know? I just go to the programming guide or whatever and learn everything. I just sit down and go through it. So what I've done is, again, Databrixified this. And this programming guide essentially goes through all these MLlib types. So you have a local vector. We've already been playing with label points. Label points are this features with labels. It's basically what we've been using already. There's a notion of a local matrix, and then there's these four notions of distributed matrices. So row matrices, index row matrices, coordinate matrices. Coordinate matrices, you can specify the ij entry. Index row matrices are where you can exploit some indexing structure on the row matrix. I mean, it could be ideal for time series. And in the very end, tomorrow, I'll give you like stuff that I would do if I had another 12 hours at my disposal, including the latest time series libraries from IBM, which are quite not open sourced and stuff. But okay, and I think what I'm doing here is, I'm not saying you need to do this. This is not assigned homework or anything, but I'm basically going through the programming guide so you can really understand this stuff. Okay, so yeah, so knock yourself out. So here's a labeled point. So we've seen this before. So you'll have a label and you'll have a dense vector or a sparse vector as a label point. Right? So this is kind of our usual entry into features and labels. Then local matrices. Yeah, this is basically what we've seen, our usual. So you can have MLlib matrix and matrices. So you can have a dense matrix, and now it's slightly different, you see. So we're now using matrices.dense, and then you have to specify the number of rows, number of columns, and then you specify the matrix as an array because it's a 1D zigzag indexing. So anyway, there's a lot of operations you can do. There's sparse variants of local matrices. Local matrices are very useful because they usually are expected to fit locally in one machine, so you can broadcast them and do various things with them. So you minimize, you just do one communication, right? You can also, of course, use local matrices as, what are those other variables? As broadcast, and then the one that, the one that collects information from workers. Which one?
Accumulators.
Yes, accumulators, thanks. So yeah, so these are, you can do, exactly. So then, yeah, so now this is just getting into distributed matrices in Scala. So once you, yeah, so this is, I guess, very important. So there's a huge difference in the orders of magnitude between the maximum size of local versus distributed matrices, because local matrices can only be of size int, and distributed matrices can be of maximal size long. So long is quite big, right? It's 9.2234 10 to the 18. So I mean that's the limits, right? Because we can't even represent the row of the matrix beyond that right now, but that's what big data maybe. Okay, for matrices, right? So that's how sparse. And then you use int as the maximum number of rows for a local matrix. So here's just sort of quickly dropping into the first type of distributed matrix, the row matrix. It's a row-oriented distributed matrix without meaningful row indices, right? So it's backed by an RDD of its rows. So this is good if your operations, linear algebra operations, don't really have to keep track of the index of the row. It's just whatever. In the end, you're just interested in row-specific operations, not necessarily keeping track of indices. Okay, then can be compute column summary statistics. So QR decompositions, SVDs, and various dimensionality reductions use the structure. So this is how you create it, collect it, get its size. So here's a QR decomposition. So a lot of you know about the QR decomposition. So yeah, and this is all in this world called tall and skinny matrices. Like I said, tall and skinny. Okay, so then there's also Python syntax for the Pythonists. And then this is index row matrix, and once again, so it's similar to row matrix but with meaningful row indices. It could be like timestamps, for example. So there's actually some implicit order, or we could do more clever things like we can actually index the rows using spatial structures that from sort of Marina and John's world. There are things called z-order curves where you can have a, say, 2D space. These are mathematics that are called space filling curves, so you can actually sort of do a 1D indexing of a 2D space in a nice simple way. And then you can use that 1D z-order indexing as a meaningful index for this index row matrix, which could be like, you know, every 10 square meter chunk of all of, say, Scandinavia or Europe, or the world for that matter. And then you can start doing operations with them. And now you can do meaningful things. So if you want to get into John's world of like nearest neighbor operators, then the z-order curves are perfectly designed for it. You can ask the z-order curve, find me all the nearest neighbors, and it's a pretty well-known algorithm. So it'll return the indices that are within some radius of that point, and then you can only access those indexed rows, for example. So I mean, it's up to your imagination, but indexed rows are very powerful low-level things for you know, many things. I don't know what the examples here are. Yeah, I think it's just definition construction. So then this one's like the crazy one, I think. Yeah, this one's like every ijth entry matters. This is getting close to a graph now, but without the elegance of being able to represent graphs in a distributed setting. So this means you can now say a coordinate matrix, a distributed matrix backed by an RDD of its entries. Each entry is a tuple of ij, you know, the long integer for coordinate I and long integer for coordinate j, and some value double. Now, yeah, so this is, you know, this is a RDD as a coordinate matrix, and I don't know, I haven't really used this guy beyond just getting into the programming guide and constructors for it. But that's the final generality, right? You can't get any more general than that, but that'll let you represent as large a matrix as you want, and you probably only want to represent the non-zero entries of it, for example. Okay, and yeah, so this is the block matrix. So if your matrix has a block structure, and then you want to only represent the non-zero blocks, then this guy is sort of what you want to remember. It's a distributed matrix backed by an RDD of matrix blocks, where a matrix block is a tuple of int matrix, where int is the index of the block, right? So it tells you yeah, where the size matrix, the submatrix at a given index with size rows per block and times columns per block. Okay, so it supports methods to add, multiply with another block. Yeah, so I want to throw all this out there because there are guys that are into arithmetic here, so I don't want you to, I don't know if this is useful for Dan to go to SCAN 2018 in Tokyo by taking whatever your program, you know. Anyway, that was that. So let's get back into power plant pipeline. I think we'll just be able to cover regression today, I'm afraid. So so let's attach this to our cluster. So now we saw these first 4 steps, right? So now let's get into data preparation, data modeling, tuning, and deployment. So what you can do is, I hope this just works. So you can just run this command, which is simply rerunning that notebook we ran before Pika in here. So we have all those steps already done for us. So this should just work. Yeah, I mean, I'm just being lazy and calling all of that because we need that in this notebook anyway. So then we'll continue with the remaining steps quickly. Okay. So we'll do data preparation, modeling, and tuning and evaluation first, and then finally we'll do deployment. So now, okay, let's make sure this table is here. Yeah, it's still there. And my data frame is still there. Okay, good. So now what I'm basically doing is make a data frame called dataset from the table. So This is just going back to a data frame from the table. We already have this, but let's just do this anyway. So now you see I'm bringing my vector assembler, and this vector assembler has input columns, A, T, V, AP, and RH, my features, and then it sets my output column to be features. So now this is going to, create my nice vector of features I need, right, as a new column in the data frame. That's what the vector assembler is made to do. So we'll call it in our pipeline soon. I'll skip through this a bit fast because a lot of you have seen pipeline for the other example of digit recognition. So then, of course, we have to split the data because we are going to do cross-validation. So we want to split it into 20 and 80. You can choose this with 30/70 or whatever, but I'm going to do this. So what I'm doing is I take my data set and I call this method called random split, and then I give it an array 0.2, 0.8, 20/80 split. And so that's going to be the names for split 80 and split 20. And then I'm giving it some arbitrary seed, okay, with the capital L. So this is the seed of the pseudo random number generator that's going to help me make this split. So now I have my sort of split 20, split 80, which is for testing and training. So now this 80%, so this 20% I'm going to call a test set, and this 80% I'm going to call a training set, okay? And then I'm going to use the training set itself to do cross-validation in-house, and you'll see this. So we don't have a special set for validation because we will hold out within the 80% and do cross-validation to determine the penalty parameters. So then my test set I count, I got 1966, I guess, still, and this is 7602, my training set. Okay, so I will not let the algorithm see the test set at all. So this is how my data set, overall data set looks like, right? And this is how my test set looks like. And my training set looks like with just the top 3 elements. So it's just the same data set split into random blocks of 20 and 30, 20 and 80%. Now for linear regression, I just import all these things, and remember, the nice thing here is we have this MLlib pipeline. So now I'm going to create an immutable called LR for linear regression, which is just a new instance of linear regression. And I just explain the parameters that are there by default. So it's going to use some, the default is 0 for this elastic net parameter. So the penalty is an L2 penalty. So I'm in this ridge regression setting, okay? And that's the parameter I think we will be tuning down the road. Okay, so let's continue with this. So now I'm setting my prediction column to be predicted PE. This is what I will, once I train my model, that'll be the name of the column for prediction. And I'm setting my label column to be PE. Remember, this is my Y values, what I'm trying to predict. It's the power output. That's my label column, and then I'm setting the maximum number of iterations to 100. That's for the stochastic gradient descent algorithm, or stochastic variant. So it'll stop after a maximum of 100 hops down the slope. And then now I'm setting the regression parameter to be 0.1. I think. Sorry, set regularization parameter to be 0.1. That's the lambda, I think. So now I made my pipeline, LR pipeline, to be new pipeline, and then LR pipeline, I'm doing set stages, just like before in digits example, and then I give it an array of different parts that the pipeline is made of. So I give it the vectorizer, which does my it creates my column of features from the specific feature input columns. And then I pass that to the linear regression model I just set here. So now all I have to do is take the pipeline and do dot fit, because this dot fit will be applied to what comes out of the pipeline, which is a linear regression model. And I only pass it the training set data, right? So this is done, and this is essentially how the equation would look like, with all the intercept and all the coefficients for each. So now I can ask, what's the coefficient? Sorry, the intercept. It's 427, and what are the weights? And that's basically my, I have 1, 2, 3, 4 different features, right? Yeah, so we can just ask, I can ask dot columns will give the name of the columns, and I'm filtering it by every column that's not the power output, so I know it's the atmospheric temperature, whatever, vacuum, pressure, relative humidity. Those are my 4 coefficients that this thing is throwing at me. I don't know. So then, yeah, so I'm just basically taking my weights, and then I'm sort of coupling of these columns. This is, I don't know, unnecessary Scala muscle flexing, but I just want to associate the coefficients with the column. And when there's more than 4, this will be very helpful, right? So then I'm just sort of cooking up what is the equation. It's a string, and this is how it looks. So y is intercept minus coefficient times whatever. Okay, so this is my linear regression equation. Just string manipulations. So now what we want to do is see how well so let's look at the predicted columns. So now what it has done is it has not built the model with this, and then it's taken these built model, the intercept and coefficients, and then taken simply these 4 values and see how well it fits. So this is our prediction, right? So this is how far the plane is from the actual data. So it's kind of close. But then we want to formalize it. So the usual metric is called the root mean square error. So we basically, and these are sort of standard regression metrics. So this is a way to measure how well your model fits. So what I'm doing here, I'm creating a new instance of this thing I imported called regression metrics. And then I'm taking my predictions and labels, and I'm only selecting the predicted PE and the actual power output, and converting to RDD, mapping each thing that comes there. So the first one as an instance of double, the second one as instance of double, and that's going to be my metrics. So then I can ask, what is the root mean square metrics? Root mean square error. So it's 4.6 something. What's the explained variance? And there is a lot of what is R squared, and so for those of you who know this. So these are just various ways of measuring how well the model fits to the data. Okay. So now what we want to do is it's generally a good model. If about 68% of predictions are within 1 root mean square error, and 95% are within 2 root mean square error of the actual value. So let's see if that's true. So these are sort of basic things one wants to find out. So first we calculate the residual error and divide it by the RMSE from the predictions and labels. That's what this is doing. And then we can simply do a SQL statement for this. So I just made a little table. So what this is showing is that my actual power output is here. This is my predicted power output. This is my residual error, and how far is it within RMSE? So to do the evaluation, I can just select within RMSE from this table and see how it's spread out. So does it look like whatever 68% is within 1 absolute deviation of 0? Seems pretty good to me. So, and this is what this statement is trying to find. Right? So this is within 1, and 30% is in 2. So it's not a bad model according to textbook definition, right? It's not doing too bad. Okay, so we have about 70% of our training data within 1 RMSE and about 97% within 2 RMSE. So the model is pretty decent. So of course we will say we want to improve this. So now we're going to get into tuning and evaluation. So let's bring in our parameter grid builder, right, and cross validator. So these are parts of the ML tuning pipeline. And remember when we had the decision trees, we did exactly the same. We had a param grid builder. And I'm not sure if we had cross validator, did we? We did something. But you know, there the grid builder, the parameter was the maximal depth of the tree, right? So we set it to be a bunch of depths, and then we somehow did cross-validation. I think we did cross-validation. I don't remember. So let's get that. So now we're going to have my evaluator class set up to judge the model based on the best root mean square error. This is going to be like my judge, okay? So this means I can have an arbitrary model that does the prediction, and I can take the prediction and see the root mean square error. So it doesn't matter if I use linear regression or ensemble method or gradient boosted regression trees. I have the same metric to compare different models. That's kind of what I'm setting up here. And so now we treat the LR pipeline as an estimator, right? Because you know, because we're going to wrap into it the cross-validator instance, which means we're going to use the 80% of the data to do our cross-validation. And we're going to do what's called a threefold cross-validation. So for those of you who don't know this term, so cross-validation is this basic idea, where if I have, say, my 80% of my data like this, and I'm doing threefold cross-validation, what I'm actually saying is I'm going to break this into 3 blocks somehow, some randomized way, and then I'm going to use this much of the data to actually do the training, you know, the real training, and I'll use this much of the data to check against that, you know, so this is to decide what should the penalty be. And then I'll do this 3 times because this is the first time, right? The second time I'll use this for training and I'll use this for validation. And the third time, ooh, this is that. So I'll use this for training, right? Training, validation, validation. And then I'll use this bit for validation in the third time, right? So this is 1-fold, 2-fold, 3-fold. So, you know, you can do 20-fold, whatever. So this is a way of like simply using the training data itself, different subsets of it, and holding off things in it. And this is another standard way of finding out the hyperparameters. Okay. So a cross-validator also requires a set of estimator parameters, which we set next. So here you see I'm because this lambda cannot be too big, you know, so I'm basically taking this regularization parameter lambda to go from 1 to 10, and then I'm dividing it by 100, so I'm getting these values from 0.01 to 0.1. This is from experience. Why am I doing this? Right, you have to play around for the right parametric form, but usually for ridge regression, that's sensible. Right, so and then here's my, because also remember, when lambda is 0, we're back to ordinary least squares, right? There is no penalty at all, so I'm not interested in it. I want to penalize it. Yeah. So now I have my parameter grid builder, where I've added the grid, I've added my regularization parameter, and this reg param is the grid itself. So the second argument is the grid, and the first argument is what do you want to be the hyperparameter. And then I have my cross-validator I declared above. I'm passing in the parameter grid. Right? So that's it. So this all happens now. Let's see. So now all of this is happening for you, right? Which means the fitting the model for a given lambda on all those 10 of them, 3 times cross-validation, blah, 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 right? And so it's going to return to you the best of these 10 lambdas over a 3-fold cross-validation, and it's done. And the beauty is this will scale to very, very large data sets. Of course, you have to, you know, if you want to be locked into Databricks, you have to buy their professional shard and pay for AWS, but you can just, yeah, you can just rip this and do it on your own too. The code will just work. So, okay, so then there is also, I want to point out that in addition to cross-validators, Spark also offers something called train validation split for hyperparameter tuning. And this way of doing hyperparameter tuning only evaluates each combination of parameter once as opposed to k times, okay? And this is something we may have to do because this is a baby data set, so we can take 3-fold cross-validation, but for very large data set, it's way too expensive to do this multiple cross-validations. So in that case, all you'll do is you'll take the test set, the training set, and the validation set, and hope to whatever, God or whatever you want that this is okay. because you won't have time, and then you will only just hit this against your hyperparameter, each value for the hyperparameter once. So that's important for large complex problems, and that's already built in as well. Okay, so now we have tuned, so let's see what we got for the tuning parameters and what our root mean square error was for versus our initial model. So now our our square for the best model is here. It's 0.9311, and our root mean square error is 4.599. So okay, so that's what that is. So I don't know, did it change much? What was the root mean square error before we did the cross validation? Do you guys remember? Oh, this is the older one. Oops. Yeah. No, it's the same.
No, 8.6.
So did it improve or it decreased? Okay, well, that's so oh true, because I think I just sorry, I think I remember. I did this and then I fixed the best one upstairs. Sorry. So but if you don't know, it's 0. Remember we set a regularization parameter explicitly to be 0.1 or something. So here let's explore other models to see if we can predict the power output better. So now I kind of want to explore this world. So linear regressions are great, but the sort of really big rave for the last decade was random forest, actually, since the late 80s, right? So now let's get into decision tree regressors. So we only used decision trees for classification last time. We can also use decision trees for regression. So let's do that, see how well this does. And we'll build a machine learning pipeline for this. So all we have to do is val dt, new decision tree regressor, and then I'm going to set the label to be PE, prediction column to be prediction PE, set features column to be features, set max bins to be 100. Remember, max bins is the discretization parameter for random forests. That means it takes the feature space and discretizes it into this 100 bins. So then I'm creating my pipeline, and the beauty is I can reuse the vectorizer from before, from the linear regression. Remember the vectorizer, because the data set hasn't changed. So now let's do that. That's my DT pipeline, decision tree pipeline. And the other beauty is I can just reuse the cross validator, and this is very important because you can be sure that you're using the exact same cross validator across model families, right? Because you don't want to mess around with that, because so many bells and whistles. So here's my param grid builder. This, of course, has to be model family specific, right? So here I'm building my param grid to be, so I'm adding a grid, and I'm having my max depth as my parameter, just like the other day. And then I'm only trying 2 depths, 2 and 3, okay? And so I'm building my param grid now for decision trees. And then I'm reusing this. I'm doing cross-validation on this new parameter grid. So my DT model is simply crossval.fit training set, because I'm only throwing the training set at it. But now this will do the entire decision tree for us with cross-validation. Right? So now let's look at the best model that came out of these 2 depths. So depth 3 with 15 nodes apparently is the best tree. I'm just asking it to report the best tree as a string, and then it gives you the if-then statements, right? Feature 0 was, I forgot, temperature or something. Right, so it's telling you where it should split and blah, blah, blah. So now this is just a visualization of it. So, it's just the depth 3 tree, and it's telling me which which feature column to split on and where to split on, and what the mean value for that leaf node is. So it's really just a simple function, It just splits things up in 4 dimensions, I guess, and then just assigns constant values to it. And it simply looks at the points in that chunk and simply reports the mean of all the points. That's basically regression decision trees. Okay, let's see how our decision tree model compares to our linear regression model. So so now the root mean square error is 5.22, so it's not as good, right? So it was slightly worse than our linear regression model with 4.6 for linear regression and 5.2 for decision trees. So then this is just a teaser because decision tree is only one. So now if you have a forest of them, a whole set of trees, that's called, ensemble methods, right? And ensemble methods are, one of the most generic, nice one is called gradient boosted decision trees. So you learn this over like multiple lectures in a proper machine learning course, right? But so I think the cell below, at least on a community edition, will take 16 minutes because there's a lot going on. So we can kind of get into it. I highly recommend this link. I don't know if it still works. So it's a very, very nice explanation of gradient boosted decision trees. Okay, so what's the idea? So gradient boosting, or GB, is a machine learning algorithm developed in the late 90s that is still very popular. It produces state-of-the-art results for many commercial and academic applications. So my recommendation is always throw linear regression, gradient boosted regression trees and things like this in this very simple cross-validation pipeline at your problem before you start inventing your own methods, because if you can't beat them, then it's not a bad idea. Okay, so here's the main idea. So you have a split along some dimension, right? And then you put some value for x and y. So I told you these are called simple functions in mathematics. So you partition the space according to the tree and then assign values to it. This is one decision tree, right? So and usually this blue height is coming from all the points that landed there, the mean value of all the points that landed in this x1, x2 world, right? And the same way, the mean value of all the points that landed in this bucket is higher. So that's why you get this. Okay. I really don't know. This is quite fancy visualization. So this is tree depth 1. I'll make this smaller. And then let's see what happens if I can increase the depth. So now I'm splitting twice, so you can start seeing like it's it's taking a more refined form, and this is essentially right, because if the underlying function is continuous, these things, or in general, these simple functions will really approximate them well. So that's kind of what's a single decision tree with a lot of maximal depth can do, right? Let's look from above. What is this? Ooh, cool. So okay, so that's, and this is looking under its skirt or something. So anyway, that's not enough, right? What we now want to imagine is a whole ensemble of them sitting next to, superimposed, and that's somehow we want to extract from that. How the tree is built, okay, kind of. So gradient boosted visualization is here. So this is the result of combining 100 decision trees. So each decision tree is built separately and then they're combined, right? So I don't know what this, is there a play button or something? Yeah. Yeah, so I think, so it's interesting, right? You see with depth 4 already, this is so much more soft compared to one decision tree of depth 4, right? Think about this guy, and let's sort of turn him around to, you see one tree can do a lot, right? But lots of trees can do a lot more, right? That's kind of the main idea. It's a bit more than that, but yeah. So what's gradient boosting? So what's nice here is, so the gradient boosting builds on an ensemble of trees one by one. Then the predictions of the individual trees are summed, right? But the way it does this is kind of interesting. The next decision tree tries to cover the discrepancy between the target function f of x and the current ensemble prediction. So it's always, the next decision tree is always going after what was not explained by all the decision trees up to now, right? So it's sort of hunting the unexplained. It's kind of so it decomposes the underlying function into this very nice form. That's basically the main idea. Okay. I know it's decision tree in 1.5 minutes, right? But you get the idea, right? You don't need to really. You have to spend time to really properly understand it. But so let's get into gradient boosted regression trees for the same problem. I'm essentially doing the same thing. I create something called GBT, which is a instance of the new GBT regressor. I set my label column and prediction column features, set seed, set max bins, and set max iteration, right? So these are all various parameters for the thing, and then I'm having the same pipeline. I set stages. I'm still reusing the vectorizer, but now I use my GBT model, and the cross validator is the same, because remember, I'm just going to be playing with the maximal depth parameter, because that's a common parameter for decision trees and gradient boosted.
How many trees have
I don't know what it does by default, so we'll see. So yeah, I think there's some exercise on diving deep into the docs to figure out all these other parameters. Let's see. I'm taking some defaults, right? I'm not specifying the number of trees. Yeah. Oh, right. And I told you this will take a long time on a community edition. But you kind of pay for electricity but the performance will be way better, right? So if you look at the root mean square predictions, this is going to be really, really good. And I forgot what it is. It'll be an improvement, okay? Yeah. Does anyone have the output of this? Oh, maybe I killed it. Yeah, well, anyway, we can let it run. But it is good. So yeah, it says, so our best model is in fact a gradient boosted decision tree, which uses an ensemble of 120 trees, maybe that's default, with a depth of 3 to construct a better model than a single decision tree. So it's not a universal fact, but for fairly complicated data sets, remember we saw all these pairwise correlations between various features, and it was not very clear. There was a lot of blobbiness and stuff like this. In general, these things can fit functions a lot better than linear regression, because linear regression is just sticking a hyperplane in 4D hyperplane to explain everything, and that's can only tilt. Yeah, it'll capture more nonlinearities and more general functions. That's right. So the last step is deployment, and so let's see. Man, this is so hard to teach you guys, because it's all okay. I'm not teaching. I'm just sort of excursion, right? So the deployment part is actually the last main thing. I won't run these cells, but I think they should work. So we've now found, okay, we've taken this data, we want to do regression, we walked through quite a few things, and then we said, okay, let's actually get into cross-validation, and then use the same metric called the root mean square error and compare across different model classes: linear regression, decision tree, gradient boosted regression tree, and then for each case we applied the right parameter grids and did threefold cross-validation and so on. So finally, what's the main thing? You want to serve this data to your client, right? So to serve this data, you need to be able to actually someone will be asking you questions live, and then you need to somehow take this in a Spark stream or something, and then reply with your prediction from your best model up to now. And that's exactly what Spotify does, right? That's what everybody does. So these are standard model serving problems, right? So this is called deployment problems. And if you take this course that Andreas Hellander teaches in IT in this building right now, you will really get more into the engineering end of it, because that's not a trivial thing. So I'm kind of showing you like, well, it's the same thing, but you have to do a bit more than just. So I won't run through all these cells, but what will happen in the end here is that we will do a deployment, and in the deployment we will simply be getting stuff in Spark streams. So people will be asking you stuff, and then you can actually update them in live, whatever. So you can tell them what your prediction is in live, right? So that's what the last part of this thing does actually. Yeah, now I'm calling all those notebooks. So yeah, maybe I should have just made one notebook. So yeah, this is basically how it's going to look. So yeah, you see, remember SSCs, so creating func. So we create a Spark, a streaming context, and then we essentially, we have to only have one streaming per cluster, and then we can receive data from the client, and then reply. Make a RDD, and then we whatever. I'm just sort of creating a queue to make a request by sleeping every 5 seconds, just to imitate customer behavior or whatever, the client behavior, and then we can serve back the prediction for these requests. So that's essentially what sort of trying to do here. Right? You can see predictions. So if you do this later on, you will start seeing the predictions, this table start filling as new queries come in, and you can see your predictions. Yeah, so that's there. You guys know about Spark streaming, so it's just this extra layer you add on once you build your model. Sorry to rush. I really kind of, yeah, I don't know. Should we do this? Should we do this tomorrow? This is okay. This is the last thing I wanted to throw at the models. Of course, my plan was super ambitious. I was going to do all of GraphX as well. We'll definitely do GraphX tomorrow, but you guys need to be fresh. But this thing, we have like 11 minutes. So this is a very nice example. We could also start from tomorrow. What is sort of interfacing into sort of John and Marina's world. So now we have GPS trajectories with accelerometer readings, and we want to do a time series model. And this is actually a great talk by Mira, French woman, data scientist. And I just basically asked her for her original data sources and stuff. So what she's trying to do is, her buddies, watch this video if you're bored tonight. It's quite good. And they just did various activities, like someone jumped, and and then there's the timestamp, and then this is just the XYZ accelerometer readings from their cell phones if they're jumping or sitting, standing, walking, running, right? So this is a very basic problem in like geospatial analytics, like what is the activity of the individual, right? So I thought this will be a good example because she's using random forests, right? Which is an ensemble method, and then it has a nice time series element because Marina was asking about time series, right? And the problem is by looking at some. So if you don't know what the activity, you train and build a model somehow, but you don't know what activity it is, and you start seeing data from some user on just this accelerometer values. The question is, can you predict what they're doing right now? That's the very concrete problem, right? So yeah, and that's what this thing is. Should we do this tomorrow, or what do you? Yeah, sorry, it's like I had way too much fika, so I'm like sugared out. Boom. But I know I rushed a lot, but because there's a huge variance in the skill levels and everything, I mainly threw that there because tomorrow I'll mostly be focusing on operations, on what you can do with Magellan and OpenStreetMaps and GraphX, and because at the end of the day, I will not be able to do these kinds of models on what you're going to learn that you can do in a scalable way. So you can put these together on your own easily. It's kind of that. Yeah, let's meet tomorrow, 8:30. Are there any questions generally? Yeah.
Because the Hyoer-parameter, when you do the linear regression, you have this lambda or alpha,
Yeah.
which is regularization.
Yeah.
So is it taking into account outliers? Or like I would like to have an intuition about why.
Well, so I mean, the intuition is, Marcus can give you more intuition. I mean, you have to look at the problem, right? So the weights, the betas, or whatever you call the slopes. So when the slopes are allowed to be arbitrary numbers, right? You know, I mean, they can really, I don't know, kill the signal, or so you know, this is one way of penalizing the model complexity. You're not allowing them to be arbitrarily large. You're saying that if you are very big, then I will penalize you based on how big you are, which has this contraction effect. So all the betas try to like be close to zero. So like, you know, if some guy dominates it, there is a penalty it has to pay. I can't explain in words. You know, you have to start understanding it for 2 dimensions. You can start playing with, you know, you can throw outliers in that simulation. That's why I did. But for lasso, there is a lot more geometric intuition. Again, you have to play with simple data sets. And for lasso, I would read the original paper by Tipshirani. So yeah. So I mean, I think yeah. So this is the shrinkage and selection via lasso. This is the classic paper. So I mean, yeah. So right. So you know, if you start, I think this is free. If you get into the PDF, oh yeah, here it is. I mean, you want to read this like very slowly and go to see. He does lots of examples, small examples by hand. You know, it's a lot going on. I don't know where the examples are. It's annoying. Okay, so yeah, you know, you want to. Then he gives you these nice little. I'm pretty sure it's this paper. I read it as a grad student, right? I mean, so there's a lot of geometry involved, and you have this is L1 penalty. For L2, I don't know. Do you have anything better, Marcus? Like, how do you explain why is lambda penalizing big betas?
Yeah, well, I guess it's because when you square something big, it becomes even bigger. So it's even worse to be big, but small values are less important.
Yeah, that's yeah. I see. So because the betas control. No, but well, okay. I don't. I'm too tired because I don't immediately see why. Yeah, I guess so, because you're saying the betas, big betas will go up, but then if the data points are close to a big beta,
yeah,
your argument is busted, right? Then you know what I mean. Then the sum of squares will still be small. I'm too tired. Yeah. But you know, just do the arithmetic in 2D, man. You'll see so many examples already. I mean, I was always told that there is this shrinkage thing. I said in Untitled, there's like betas are kind of forced to be close to the origin in the beta space, you know, because the bigger they are, they have to explain the data way better because they get penalized for being big. So there is a lot of love in being close to the origin, right? The betas have to co-fight, and I don't know how to explain it. You know, it depends on them. So it's a way of penalizing. Are there any other questions? Okay, well, have a good evening.